So proceed na tayo sa ating simple strain. So this is also known as a unit of deformation. So pagde-deform ng isang material ang simple strain. And this is the ratio of the change in length caused by an applied force to the original length. So for example, meron tayong material, yan, naka-fix siya sa isang, sabi natin sa isang wall, tas meron tayong rod or steel rod. And then, meron tayong applied tensile force dito, so going to the right. And then we have this, yung kanyang subjected area. And meron tayong L, yung original length niya. Ngayon, pag once na nag-apply tayo ng force or tensile force dito, is may tendency na magiging ganito yung ating material, mag-elongate siya. So, meron tayo ditong symbol. This is what you call delta. Ayan, ito yung parang elongation niya. Ito yung pagbabago ng ating material. Diba? Nag-elongate siyang ganyan. Ngayon, strain natin, sabi niya dito, ratio of the change in length, so yun si delta, divide by the original length natin. So, we have a formula for strain. So, yung symbol ng strain natin is epsilon. Ganito yung symbol natin dyan. It is equal to elongation divided by the original length. So, kung napapansin natin, si elongation in terms of distance siya, pati si length natin. Therefore, si strain is dimensionless or unitless. So, yun lang yung ating formula for simple strain dito. So, again, this is the unit of deformation. So, pag de-deform ng isang material dahil sa na-apply na load sa kanya. So, meron tayong tinatawag din na stress-strain diagram. So, suppose that a metal specimen be placed in a tension or compression testing machine. As the actual load is gradually increased in increments, the total elongation over the gauge length is measured at each increment of the load and it is continued until failure of specimen takes place. Sa mga testing of materials natin, na kapag for example, yung sa rebar, di ba, yung pag-testing nun is due to tensile strength. Ngayon, hanggang sa yung applied actual load sa kanya is tensile, syempre hinihila siya, ganyan, hanggang sa ma-meet niya yung pinaka-maximum and then mapuputol siya or mag-fail. So, yun yung sinasabi niya dito, na actual load is gradually increased in increments over the total elongation of the gauge length natin. And then, sa pag-alam natin ng cross-sectional area and length ng specimen, makukuha na natin or ma-obtain na natin si normal stress and si strain natin. So, di ba we have a formula for normal stress? It is equal to the applied load divided by the area. So, yung previous topic natin, ano? And then, the graph of these quantities with the stress along y-axis and then si strain natin along x-axis is yung tinatawag nating stress-strain diagram. So, yung stress-strain diagram differs in the form for various materials. So, yung diagram na papakita ko niyan is for a medium carbon structural steel. Ito siya. Ayan. So, y-axis, we have the strain. And then, sa x-axis, we have the strain. And then, sa y-axis, we have the stress. Ayan. So, meron tayo ditong proportional limit, the elastic limit, the yield point, the ultimate strength, and yung ating rupture strength. So, ito yung isang example ng stress-strain diagram. So, i-identify natin or i-define natin bawat isa. So, first, we have here yung ating proportional limit. Yan. So, from the origin O to a point called proportional limit, the stress-strain curve is a straight line. So, this linear relation between elongation and the actual force causing it was first noticed by Sir Robert Hooke in 1678, and it is called the Hooke's law, that within the proportional limit, the stress is directly proportional to the strain. So, meron tayo straight line. So, ba't straight line? Ibig sabihin nun is, kung gaano nag-i-increase yung stress natin, equal lang siya sa pag-increase ng strain natin. So, yun si proportional limit. And then, sabi niya dito, directly proportional. So, we can say that stress is also equal to strain. Pero, Di ba ang ating unit sa stress is megapascal, for example. Kaya lang, si strain natin is unitless siya. So, paano kaya natin masasabing equal? So, meron tayo dito ang additional na K, which is, ito po siya, constant of proportionality, or it is called the modulus of elasticity, or Young's modulus. So, it is equal to the slope of the stress-strain diagram from O to P. So, therefore, yung formula na po natin na gagamitin is stress, it is equal to modulus of elasticity multiplied by the strain. So, ito yung isa sa mga formulas na gagamitin po natin. Ayan siya. So, proceed tayo sa next limit natin, which is the elastic limit. So, dito, papasok yung tinatawag nating elasticity. So, we have here, it is the limit beyond which the material will no longer go back to its original shape when the load is removed, or it is the maximum stress that may be developed such that there is no permanent or residual deformation when the load is entirely removed. So, again, kung natatandaan, di ba pag elasticity, once na may in-apply kang load tas binitawan mo or tinanggal mo, babalik siya sa original shape niya. Pero once na sa elastic limit, yung kumbaga lumampas ka na sa limit, ibig sabihin, yung deformation na nangyari is pwedeng hindi na siya bumalik sa original shape niya. So, yun si elastic limit po. And then, proceed tayo sa ating next. We have the yield point naman. So, the point at which the material will have an appreciable elongation or yielding without any increase of load. So, sa yield point naman po natin dito is ito yung, kumbaga pag umabot ka sa yield point, ibig sabihin, safe ka pa rin naman. Parang dito nag-start na yung deformation talaga ng isang material natin. And then, pag lumampas ka na sa yield point, may tendency na baka rin mag-fail na yung ating material. Pero, sa yield point, so yung parang isa sa pinaka-peak ng material bago siya mag-deform. Ayan. So, next, we have the ultimate strength. So, si ultimate strength, ito yung ginagamit karaniwan sa mga designs natin. Ito yung kino-consider na value for kung ano yung gagamitin nating materials. Ayan. So, we have the maximum ordinate in the stress-strain diagram is the ultimate strength or the tensile strength. Ayan. So, kung napapansin natin, so ito kasi dapat medyo mababa. Hindi ko lang siya naayos. Pero yun dun sa module natin, medyo medyo pag ganyan yan. Parang pag ganyan siya. Ibig sabihin, hindi ganun kataas yung pagtaas ng value ng stress kapag once na na-elongate na siya ng todo, di ba? So, parang, di ba si stress natin is over an area, di ba? So, kapag lumiliit ang area natin, hindi ganun kataas yung, o kumbaga lumiliit din yung stress. Kumbaga, hindi ganun kalaki yung increase niya. Kaya yung banda dito is, konti lang yung pag-increase ng stress natin. So, proceed naman tayo sa last, yung ating tinatawag na rupture strength. Ayan. So, sa rupture strength, minsan, ito rin yung kino-consider for sa isang design. Ayan. So, itong mga to is talagang mas magagamit nyo to on your design subjects. Ayan, mas ma-elaborate doon yung mga terms na to and mga problem solvings regarding this. So, we have the strength of material at rupture. This is also known as the breaking strength. So, sa rupture strength, syempre, ito na yung part na talagang meron na yung pwedeng maging fail na yung ating material. Ayan. So, next, meron din po tayong elastic and plastic range. So, dito, the region in the stress-strain diagram from O to P is called the elastic range. Ayan siya. So, ibig sabihin, dito sa range na to is pwede pang bumalik sa dati yung ating shape after ng applied load natin. And then, next region is from P to R naman or yung plastic range. So, plasticity, ayan. Pwedeng hindi na bumalik sa dating shape once na meron na tayong na-applied na load. So, proceed naman tayo sa tinatawag na modulus of resilience. So, this is the ability of to absorb energy without creating a permanent distortion. So, this is sa stress strain diagram natin is it is from O to elastic limit. Ayan. Yan si ating modulus of resilience. Next naman po, we have the modulus of toughness. So dito, it is the ability to absorb energy without causing it to break. So, si modulus of toughness, ang kino-covered naman niya is yung kabuuhan po. Ayan. From O to R sa modulus of toughness natin. So next, we have here the working stress, allowable stress, and factor of safety. So we have here yung tinatawag na working stress is defined as the actual stress of the material under a given loading. And then the maximum safe stress that a material can carry is termed as the allowable stress. So yun yung tinatawag nating allowable stress. So si allowable stress natin should be limited to the values that not exceeding the proportional limit. However, since the proportional limit is difficult to determine accurately, yung allowable stress natin is taken as either the yield point or ultimate strength. So, kaya ganun yung, and then divided by the factor of safety. So, di ba kaya nabanggit ko kanina, sometimes, or madalas, ang ginagamit na sa design is yung value or yung pinaka-ultimate strength talaga natin. And then, the ratio of this strength, ultimate strength or yield strength, to the allowable strength is yun yung tinatawag na nating factor of safety. Ayan. So, kailangan natin, so si factor of safety kasi, so doon mo malalaman kung safe ba yung ating structure o hindi. So, we have naman here are axial and shearing deformation. So, first, kay axial muna tayo. In the linear portion of the stress-strain diagram, the stress is proportional to the strain and it is given by, di ba ito yung formula natin kanina? We have sigma or stress, it is equal to modulus of elasticity multiplied by epsilon or the strain. So, therefore, di ba si stress is P divided by the area and si strain natin is delta divided by the L, then PA is equal to E delta divided by L. So, kunin natin yung value dito ni elongation, itong ating delta. So, cross-multiply lang, we will come up with the formula of it is equal to PL divided by AE. So, kung given si P and given si A, so ito yung gagamitin natin. Pero kung may given naman na tayong stress, so therefore, stress multiplied by L over E lang nun. So, yun yung formula ng ating elongation. So, magagamit natin yan later on sa ating sample problems. So, take note na this formula, the load must be axial and the bar must have a uniform cross-sectional area and the stress must not exceed the proportional limit. So, ibig sabihin ng uniform cross-sectional area is, syempre, iisa lang ang ating area. For example, ganyan. Pantay lahat yung iisang material. Pero paano kapag ang material natin, so for example, yan, is hindi siya uniform. So, papasok dito yung sa pag-integrate natin. So, sa integral, di ba nagko-consider po tayo doon ng, so, pino-control Z ko. Sorry, ayan. So, we have, so, di ba nagko-consider tayo doon ng strip sa ating integral? Ayan. So, magagamit natin po dito yon. So, kapag hindi na uniform yung ating cross-sectional area. So, proceed tayo pag ano kayong formulang gagamitin natin. So, sabi niya dito, however, the cross-sectional area is not uniform. The actual deformation can be determined by considering a different length and applying integration. So, for example, ito yung ating section. So, magko-consider tayo ng strip. We have here yung dx and y niya. Y is for the height and the dx yung kanyang thickness. So, ito yung parang magiging material natin. So, ang formula natin dyan is we have elongation is equal to P divided by E, integral of 0, limits we have 0 to L natin and dx divided by A. So take note, si A natin dito is it is equal to Ty. And then si y and t natin, if variable siya, it must be in terms of x. So ito yung formula kapag hindi po uniform ang ating cross-sectional area. So next slide po tayo. We have for a rod of unit mass. So we have here rho, hindi po pressure to density naman to. So yung density kasi minsan ang kanyang symbol talaga is in terms of rho din. So suspended vertically from one end, the total elongation is due to its own weight. So for example, ito po yun. Meron tayong rod na naka-fix siya sa, for example, sa ceiling, ayan. So yung total elongation natin is hindi lang sa dahil sa na-applied na load, kundi additional din yung para sa weight po niya. Ayan siya. So syempre, may ko-consider tayong weight. So, ito yung formula for the elongation due to its weight. Ayan. So, we have density multiplied by G, L squared divided by 2E. So, di ba, pag pinag-multiply natin si density and then, if ever na ang given is in terms of mass, ito naman yung formula natin. We have M G times L divided by 2AE. So, ito, kapag density yung given naman. Ayan. So, we have rho, or the density, it is in kilogram per cubic meter. We have the length of the rod is in meters. And then M is the total mass of the rod. We have kilogram. And then area, cross-sectional area of the rod, millimeter squared. And si G natin, so, constant ito, syempre, familiar na tayo dito, we have 9.81 meter per second squared. So next, meron din tayong tinatawag na stiffness. So small letter K po yan. So stiffness is the ratio of the steady force acting on an elastic body to the resulting displacement. It has a unit of Newton per millimeter. So, ang formula lang ng ating stiffness, it is equal to P, or the applied load, divided by the elongation. So, madami tayong may encounter na formula and kabisaduhin na lang, di ba? Mas maiging na may memorize na natin. At least pag nagsusolve, dire-diretso. So, next, proceed tayo naman sa shearing deformation. So, familiar na sa shearing, di ba? Yung pag-slide or sa mga previous topics natin. So, shearing force causes shearing deformation. So, an element subject to shear does not change its length but undergoes a change in shape. So, ano kayang ibig sabihin niya doon? For example, meron tayo ditong rectangular na section. And then, meron tayong in-applied na tensile force sa taas going to the right. And then, sa baba is going to the left. So therefore, pag nag-apply tayo ng tensile force, pwedeng magiging itsura or magkakamap tayo sa ganitong section na. Diba? Magiging ganito yung section natin. Uusog yan ng ganyan. So sabi niya dito, does not change its length. Ibig sabihin lang po nun, yung elongation na nangyari dito sa side na to is equal lang dito. So therefore, wala talagang pagbabago sa length natin. Pero, nagbago yung shape niya, di ba? But undergoes change in shape. Ayan, di ba? Naging, nakadiagonal na siya, di ba? So, yun yung ibig niyang sabihin sa ating shearing deformation. So, meron tayong following formulas dito. Kapag the change in the angle of the corner of an original rectangle element, it is called the shear strain, and ito yung formula niya. Ang ating symbol for shear strain, we have sigma. It is equal to delta S divided by L. Ayan. So, next, we have here naman the ratio of the shear stress, si tau natin, and the shear strain natin is equal, gamma pala to, diba? Is called the modulus of elasticity or the modulus of rigidity. So, ito naman, capital G. we have tau divided by gamma. Gamma pala yan. So, in terms of megapascal siya. So, next, we have relationship between the shearing deformation and the applied shearing force. Ito naman ang ating formula. We have delta S is equal to VL divided by AS multiplied by the G. So, pag sinimplify natin, meron tayo dito. Ito yung ating shear stress, tama? We have tau multiplied by L over G, where V is the shearing force acting over an area AS.